Okay? I'm going to use the two colors to indicate plus and minus. Okay? And this will be my C phase. This is where my phase propagates. Next, I'm going to interfere that with another wave. But before I do that, I'm going to angle that, an angle above the horizontal. So this is my, should do that in white. My Z now. Okay? Call that Z1. So wave 1 is traveling this way, and these are the pulses of wave 1. And apart. And the minuses are in between. And I'm going to interfere that with an identical wave, same frequency, same everything, but the other wave now is going to go at Z2. I'm going to assume that they are both synchronized, and the wave fronts of that, the pluses will be like here, and the minuses are in between. These two waves are identical in frequency, in wavelength, in propagation characteristics. They are synchronized with each other, so there is no problem when we mix them up. If we mix them up now, obviously, when you have a plus and a minus, you get a zero. Another zero here, another zero there. Wherever we have a plus and a minus, you get a zero. Obviously, my drawing is not that perfect, so you can see the zeros kind of shifted a little bit. Here's another zero, zero, zero. Wherever you have interference. If I think about these as voltages, and the potential here is zero, that means I have a whole entire plane here where I have a zero intensity. Likewise, I have another one here. In fact, there are several of those. There's a third one here, and there's a fourth one up there, and so on and so forth. According to the uniqueness theorem, you guys remember the uniqueness theorem? If you had me in undergraduate fields, that means you must have seen that theorem before. The uniqueness theorem says that if I have two problems, well, it doesn't say that exactly, that's an implication. What it says is, if I have a region well-defined, I know all the sources, I know all the material inside, I know all the boundary conditions around it, there will be only one unique solution. If I define this room, I define the sources in that room, I define the boundary conditions around this room, I have one unique solution for what happens inside this room. Okay? When you solve the differential equation and I give you boundary conditions, you end up with one solution. If I don't give you boundary conditions, you have several possible solutions. Boundary conditions reduce the number of possible solutions to only one. Okay? So, if I have two problems with identical regions in terms of sources, material, geometry, etc., and identical boundary conditions, then the two problems must have the same exact solution. So this problem here, I can claim that it is identical to another problem. Conductor here and conductor there. The region here was space. The region here is space. No sources. No sources. Zero boundary conditions. Zero boundary conditions. These two problems are identical. So the solution here is identical to the solution there. So if I have this kind of a situation where I have two parallel plates, okay, indefinite, infinite, the field solution inside would be of this nature. That's one possibility, right? There are other possibilities. If I were to squeeze that and work this out with the second one, all right? Or if I squeeze this picture out and work with the third set of zeros. So actually, as it turns out, that there will be several possible solutions because these boundaries here could fit this solution, could fit that solution, could fit the other solution. And the reason for that is that the actual excitation is the one that determines how many of these possible solutions can exist. Because that's an open system. It's not exactly a closed system. Once I add the source and load, and I add the source and load, then there's only one solution. Right? But before that, I will still have several possible solutions because the source and load could change that angle, and therefore could change the relative position of those plates. Okay? In this situation here, that's really an insight of how the waveguide works. If you work out the wave propagation inside the guide, you will discover that basically what happens is that your pointing vector is really going along the z-axis. All right? And if these are zeros, it continues by bouncing back and forth. My angles got kind of deformed, but you got the concept. And your wave propagates within the guide. And the propagation in this case will have a different wavelength. Look at the wavelength now, the distance between the peak and the peak. These are two peaks. And that's your length and the guide. All right? Your phase velocity in the guide is going to be different. Your wavelength in the guide will be different. Your beta of the guide will be different. Your characteristic, all these kind of things you can derive as a result based on this angle of excitation, which the source determines. The angle of excitation is determined by the source. And obviously, the boundary conditions play a role in this regard. So, what's happening here is that we can make propagation without having two wires. Right? What's stuck in the background of our minds is the transmission line carries the signal because we have two wires. That's not true, because waves don't propagate in the wires. The wires guide the waves to propagate within. Right? You know, when we start with electrical engineering, You told us this wire carries the plus current, this wire carries the minus current. That was an oversimplification, a circle simplification to what happens. And that's what happens at DC. But waves don't need those wires. Waves can propagate in open space. The wires do confine the wave or guide them to go a certain way rather than the other. And the waveguide is one of those. Obviously, since waveguide cannot propagate DC, we can expect it to have a certain low frequency cutoff, below which you can't send a signal. And that low frequency cutoff is going to be part of the analysis that we'll do in the waveguides. So what do you think? Should we continue with waveguides or get back to scattering parameters? I'm still debating.
We already covered scattering.
Huh?
We already covered scattering.
We did only one quick lecture, so the lab guys can have a feel for it. No, there's more to it than just that. At least maybe 3 or 4 lectures on scattering parameters.
Should we scattering parameters and then after the test have a waveguide?
That's what you're suggesting? Okay. What about the others? Are you okay with that? This is going to be math intensive. The waveguides, lots of math in their development. Go back to Maxwell's equations. What's wrong? You don't like Mr. Maxwell? The guy did a wonderful job for all humanity, and he gets your company here. All right, we'll see you on Monday.